Yo, what's up everyone? Today we're going to be doing the descriptive slash laboratory section of the 2022 USNCO local exam. So this is from question 7 through 12. Let's get started with question 7. We're asked which salt gives a colorless aqueous solution. So this is testing your transition metal ion colors in aqueous solutions. So let's go through our answer choices to see which one is not going to be colored. A, we have sodium perchlorate. Sodium perchlorate doesn't have a transition metal in it, so it can't really be colored. Therefore, it's going to be colorless. So our answer is A, but let's go through the rest to make sure that A is the right answer. B, we have potassium chromate. We have that chromium ion there, and specifically it's the chromium 6 plus, so this is going to be like an orange solution, so that can't be right. C, nickel nitrate. It has that nickel, so it's going to be kind of a green color, can't be C. And then D, we have copper sulfate. It has that copper, and then that copper is going to be make it like kind of light bluish. Yeah, this is just knowing your transition metal ion colors. Maybe memorize those. Okay, let's go to question 8. 100 ml of a 1.0 molar solution of hydrochloric acid is gradually added to a stirred mixture containing 0.01 mole calcium hydroxide, 100 ml water, and a small amount of phenolphthalein. Which changes are observed? 1. The mixture changes from colorless to pink, and 2. The mixture changes from cloudy to clear. Okay, so in this case, we have an acid-base neutralization happening with the hydrochloric acid and the calcium hydroxide. And so calcium hydroxide has a 2 here. The thing is, our phenolphthalein is going to tell you your pH. It's an indicator. So if your pH is really, really low, it's in like the 0 to 3 range, it's going to be orange. If you're in like 4 to 7, it's colorless, and then 8 to 10, it's pink. But then after that, like 11 to 14, is colorless again. So it's going to start off being colorless. That's because the calcium hydroxide is going to make it really, really basic. But if you notice, there's a lot less calcium hydroxide than hydrochloric acid. In fact, we have 0.1 moles of hydrochloric acid and only 0.01 moles of calcium hydroxide. What that's going to mean is that the hydrochloric acid is going to neutralize the calcium hydroxide really, really fast. And after that, the hydrochloric acid is just going to be increasing the pH of your solution. So what's going to end up happening is that you have 0.09 moles of hydrochloric acid that just doesn't get used up in the reaction. And considering that we only have 200 mils of our solution here, that's going to make the pH come out to like in the decimals. It's going to be like less than 1. And when phenolphthalein is in a solution where the pH is like 0 to 3, you have kind of orange color. So 1 doesn't really make sense. The mixture changes from colorless to pink. If the pH was around like 8 to 10, maybe you would be pink, but you're not. So 1 is wrong. 2, the mixture changes from cloudy to clear. The thing with this is that calcium hydroxide is only slightly soluble in water. So that is going to explain why the solution would be cloudy. But afterwards, you have the hydrochloric acid neutralizing all of it, and then the hydrochloric acid dissolves in water. So you're going to have a clear solution. So you do go from cloudy to clear. So the answer is B. All right, let's go to question 9. Below is shown a section of a burette filled with titrant before beginning a titration. What initial volume should be recorded? Remember, the thing with burettes is that they are kind of inverted, so the top numbers are lower than the bottom numbers. So you are that's like the 1.2, and you go a little below that, that's like 1.26. And that's answer choice B. All right, let's go to question 10. Titration with aqueous triiodine solution to a starch endpoint would be least suitable for which determination? For this question, just remember that we're doing a titration, and titrations are helpful for finding concentrations of compounds. So let's go through our answer choices. A, analysis of nickel content in a nickel-copper alloy. When finding the concentration of a certain metal in an alloy, you have to just heat it up. You can't really use a titration to find the concentration because they're like physically bonded together. So you can't really use a titration for A. So A is like a promising answer. Let's go through the rest to make sure that they're wrong. B, determination of ascorbic acid concentration in a vitamin C tablet. My bad. That is something you would use a titration for. You're finding the concentration of a compound within a bigger solution or whatever. So B wouldn't make sense. C, measurement of sulfite ion concentration in white wine. Same thing, you're finding the concentration of a compound in another substance. D, determination of waters of hydration in a sodium thiosulfate sample. In this case, to find waters of hydration are usually just the water molecules that are bonded to a compound. And the way you usually find the waters of hydration is by just heating up the sample. You can heat up the sample and get rid of the water, or you could find the concentration of the sodium thiosulfate and then use that to find the waters of hydration. So in this case, you could find the waters of hydration by finding the concentration of sodium thiosulfate and then subtracting that from the entire sample. So D, you could use a titration for. Let's go to question 11. Which liquid will not react with metallic sodium? This is like a classic lab question. Metallic sodium is really, really reactive, so you don't want to leave it out. It'll react with almost anything. And the thing that we usually store it in is mineral oil. Mineral oil prevents it from reacting. So you want to store it in mineral oil. Metals like sodium that are really reactive, you want to store that in mineral oil. That'll help it from not reacting. All right, let's go to the last question, question 12. The molar enthalpy of solution of a salt that dissolves endothermically in water is measured in a coffee cup calorimeter by weighing a known amount of distilled water into the cup and measuring its temperature. Then adding a known mass of salt to the water and measuring the temperature after the salt dissolves. If some water is initially present in the cup before the weighed amount of water is added, what is the effect on the experiment? So we're trying to find the relationship between the calculated delta H and the true delta H. Remember, for delta H under constant pressure, it's just going to be your heat. It's going to be the heat of reaction. And the heat of reaction is mc delta T. Let's see which one of these is going to affect it. C is not going to change. C is a property of your water. C is not going to change. Your M does change. If your M is higher than it should be, then that means your change in temperature will be lower than it should be. So if you're calculating a change in temperature that's too low, then that means you've added too much water. So since you have more water here than you really should, then that's going to mean that the change in temperature that you record is going to be lower than it should be. And of course, you're not aware that you're adding more water than you should, so your M value is lower than it should be. Your temperature value, change in temperature value, is lower than it should be. So the change in your delta H that you calculate is going to be less than the delta H that is really true. So calculated is less than true. And that is answer choice C. And that's it. That's the entire section. I hope this was helpful. I hope you were able to learn something, and I hope to see you later. Thank you.